delta x would be defined as the difference between a and b, so b minus a, divided by the number of subintervals that we want. So divided by n. All right. So that's the very first thing you have to do. Define your delta x. Then label your endpoints, draw vertical lines creating rectangles, because rectangles are the easiest geometric figures to find the areas of. So if we can break up whatever the region is into rectangular areas, then we can easily find the area of each individual subinterval, and then take the sum of those individual areas later on. All right. So that's what really all this remaining stuff is kind of walking you through. All right. So it's a lot of words and details to kind of get across a pretty simple idea. Is that you're taking a curve, you're breaking it up into sub-intervals, creating rectangles, finding areas of those rectangles, and then adding them all up. All right. There's benefits and there's drawbacks to this approach. The benefits are that you can get a good approximation sometimes of the area between the curve and the axis. The drawback is sometimes there's going to be leftover areas that will lead you to what we call an overestimate or an underestimate. Right? So on the left-hand side here, you can see that there's definitely an underestimate. So if I find the area of these rectangles, I'm leaving off little triangular regions here that would account for some of the area between the curve and the axis. So I'm neglecting those. On the right-hand side, I'm overestimating. So if what we did was if we found areas of rectangles that were contained within the curve and then beyond the curve, but then what that would actually give us would be, it would tell us a bounded region for where we know the area would exist. All right. So if we know that the area of the rectangles that are contained within the curve are an underestimate, and the ones that are beyond the curve are an overestimate, then the true area has to be somewhere in the middle. All right. Directly in the middle, not necessarily, unless it's a constant rate of change, but at least we know it would be in that interval. Right? And if we can get those rectangles to be skinny, like really, really skinny, then we'll get a truer and truer estimate of that actual area. Right? So these are pretty wide rectangles, but if they were infinitesimally wide, then it would be a spot-on estimate of what the actual area under the curve would be. All right. We say area under the curve. It's kind of a misnomer, but what that represents is the area between the curve and the axis. It's just a lot easier to say area under the curve than area between the curve and the axis. All right. So we'll dive into an example. Draw a quick sketch. Keep it simple. Y equals x squared on the interval of 0 to 2. Crikey. So just use your line draw tool to just draw some axes. Oh. Yeah, you could. I got a whole bucket of them there if you need it. I mean, they're not as cool as my legit one right here. So I'm going from 0 to 2. All right. With n equals 4, all right, and it again is the number of subintervals. Plus. All right, the number of subintervals are the number of rectangles that we're going to create. All right, so 0, 0 would be a coordinate because we're graphing y equals x squared. The first coordinate here, other than 0, would be 1/2, and then 1/4. But I'll worry about the y's in a second. Then 1, 1.5, so 3/2, and 2. All right, so we're going to max out at 4. So I'll set up my graph to go as high as 4. 2, 3, 1. 9/4 is what, 2 1/4? Looks like meh. All right, I'm going to label the coordinates. 0, 0, 1/2, 1/4, 1, 1, 3/2, 9/4, and 2, 4. Alright, so all of that was pretty much gleaned from the problem, but we haven't really addressed the area part of it. Okay. Now it said find the upper and lower sums for the region bounded, so it's like the question of what are the upper and lower sums representing? They're representing the areas of the rectangles created depending on certain circumstances. So we'll go through that in a second, but it's a very procedural approach, but it all starts with the graph, so that's why we take into that first. Find delta x, which is b minus a over n. Fun fact, we already figured that out. All right, so my pen. So it's 2 minus 0 over 4, so 2/4, 1/2. Which happens to be the step along the x-axis. All right, so the individual lengths along the x-axis is equal to 1/2 unit. But that came from the idea that we were going from 0 to 2, and I wanted to break it up into 4 equivalent subintervals. All right, so it just kind of naturally worked out that way when I was creating the graph, but now it's a more procedural idea. All right. So what we're looking for when it says left to right, it says values on the x-axis used to find rectangles. We call that m sub I. All right. And then we plug that into fx, and we do a lot of other stuff with that. But it all starts with this one simple idea, left to right. What does that mean? All right. What it's telling us is that we're starting on the leftmost part of the graph and working our way to the right. Specifically, it's telling us that the upper left vertex of the rectangle is on the curve. I kind of painted myself into a corner there. All right, so I want to create rectangles that are going to actually touch the curve in some capacity, but I only want the upper left-hand corner of the rectangle to touch the curve. All right, so that's what I'm going to do here. I'm going to start off with the first point, and I'm going to draw a rectangle such that this is the upper left-hand corner of that rectangle. Well, the only way I could draw that rectangle would be if it was a rectangle with no height. All right, and it would span the subinterval with the width of 1/2. All right. Now the second rectangle needs to have its upper left-hand corner at the coordinate 1/2 1/4. So it would have to look like this. All right. The third rectangle would look thusly. And I could get one more rectangle in here before I run out of space. All right, so I could find the areas of these 4 rectangles, but it's going to be an underestimate of what the area between the curve and the axis will be, because I have all these little gaps here. Right? Those are going to be neglected in the area computation process. Right? But I'll get a sense of what the area would be. Now you can see that if the rectangles were skinnier, you would cover more of those gaps. Right? And so you would end up with a truer estimate of what the overall area would be. All right? So the connection between that and integration will come tomorrow. All right, but the m sub I values are the x values that are used as the upper left-hand vertices of your rectangles. All right, so m sub I would be 0, 1/2, 1, and 3/2. So then we plug each of those x values into the function to get corresponding y values. So really what we're looking for is f of m sub I. We already figured those out when we plotted the points. So 0, 1/4, 1, and 9/4. Now, just kind of going back to the diagram, if I wanted to figure out the area of each of these rectangles, I'll just do it for one of them. And then you'll see why the procedure makes sense. I'll just pull it in here. If I wanted to find the area of any of these rectangles, what I'd need to do is find the area of the length of the base and multiply that by the height. The length of the base in each case is 1/2. The height is whatever the y value is for each of those important x values. All right, so the y value is 9/4. If I want the area, I would multiply the two. So 9/4 times 1/2 would be 9/8. All right, so might as well just box in the whole thing. All right, so what I would be doing is taking whatever I would get as a y value for the corresponding x, multiplying it by the length of the base. All right, so, but really if you think about it, that's just saying take your f of m sub I, the values that we just determined. Ah, boy, there goes that video. Whatever. That's really the same as saying, you would take your f of m sub I values and multiply it by whatever the value of delta x is, because delta x gives you the length of the base. All right. So strike 2. So f of m sub I multiplied by delta x. All right, so that's going to be equal to, so each of these values multiplied by 1/2. All right, so we're looking at 0. And that first rectangle had no height, so it would have area of 0. 1/8. 1/2 and 9/8. All right. So really, when you look at it, kind of has a little bit of a look of an integral, or what's contained within an integral. And I'll just kind of put it all together for you here, because really what we're doing, and we'll do it symbolically more so tomorrow, we're going to take the sum of the f of m sub I values multiplied by your delta x values. I'll leave off the multiplication symbol. So we're just going to add those values together. So 10/8, 14/8, 7/4. 1 3/4 you said? Yeah, same. just a little teaser of what's to come, not about to come, because it's going to come tomorrow. But if I were to just compare this to an integral, be looking at something along these lines, right? The antiderivative. Now, it's not quite the same thing because there is a limiting component involved in this, because really this is not equal to the antiderivative of f of x dx, because we know what the antiderivative of f of x dx gives us. It gives us another function. It doesn't give us just a number, right? So if I said find the antiderivative of x squared, you wouldn't get 7/4 from that. You would get 1/3 x cubed, all right? Now, you can manipulate that 1/3 x cubed in such a way that you can come up with something close to 7/4, but even still, this is related to 4 rectangles that are approximations of the true area, right? They're not exact. But we can do something to this expression to make it equivalent to this, all right? So what we'll end up doing is applying a limit to this, which would allow this expression to be equivalent to this, all right? So just by applying a limit, you would get that integral, right? So what that would be doing is telling us that if we can get that delta x to be as small as possible, all right? Basically, if we can get it to approach 0, delta x being the width of the rectangle, will include more and more of the area, right? To the point where, I mean, we can't have a rectangle with no width, it wouldn't be a rectangle. But if we can get a sense of where the area under the curve is going as the rectangular width approaches 0, then we would have a true sense of what the area under the curve is equal to, right? And that's the transition from the summation to the integral, right? So that's a cool little connection there. But for now, we're still dealing with a numerical approach.
Could it be that we're going to do definite integrals?
Yes.
Whoa. We're getting there. Wow, just spoiled it. You're going to spoil endgame too, aren't you? Yeah, man. Stop. Stop.
I watched the first Avengers movie again last night, twice.
Very good.
Twice, yeah. I'm doing homework now, so it's research for the upcoming movie, because the time travel sequences in Endgame, apparently, I mean, from what I can glean from the trailers, aka what I've heard other people say on YouTube, really amounts to the fact that, you know, like set photos and storyboard descriptions and things like that. Yeah, they're going back. And they're going back to the Battle of New York, baby.
I mean, Captain Marvel's is alive. Yes. You might have to do some research for it.
What's that? Oh, I mean, I could give you the breakdown. I'll just have to call earmuffs.
Just study all of them.
What's that?
You just spend like a week or two just studying stuff.
There was a theater. I think Molly sent it to us. There was a theater that's doing like a 59-hour
Yeah.
extravaganza.
I mean, yeah, it's called Mr. Cam's House.
Literally
So-
every single Marvel movie.
Yeah.
I want to
Like,
get
it
it.
runs. Yeah.
What are they doing?
And it's ongoing.
I can't stay up to it. But I was
Even that goes
Don't
back.
stay up for that
It's
one.
just drink some Red Bull. That's a long way.
But I was,
Movie is bad.
but the scene that I'm thinking about in Avengers is when they're on the rooftop, and Black Widow's there with Selvig, and the Hulk just beat the snot out of Loki, and he's saying, Selvig just came back to his own senses, and he's like, we need the, why can't I think of the word? The staff.
Yes.
But it wasn't called a scepter, thank you. We need the scepter, and I'm looking right at it. but then that's the last time you see it. Well, that's not the last time you see it. She uses it, and then that's the last time you see it. So after until Age of Ultron. So I was looking for the moment in that movie to see if they even thought about it way back then.
That would be absurd if they did.
There are some little moments in there where I was like, okay, you're gonna use that as your tie-in.
That would be.
Yeah, it's gonna be something else.
Imagine just like having that happen, but like by accident, just like perfect plan. God, they're good.
Yeah.
Oh, you did, yeah.
All right.
On the train.
So we gotta do all this again, but we gotta come after it from the right-hand side. So what I'm gonna do is use all the points that are relevant, but come in from the right-hand side. So I already used purple. Let me just.
I thought my eyes were just like a brown movie up and I actually had back then. Leave my antennae right here. True. It was just 60 hours of Marvel movies and then the game just comes on.
So if I come in from the right-hand side, I'll start with this point.
That's right. I thought I was like, to see focus on sickness.
Then I'll grab this point. I missed. Then I'll grab this point. I'm just going to go right through this coordinates because we know what they are now. And then I'll grab this point. All right, so you can see that in each case, we're using 1 point less than the total amount of X values that we have available. So that's something to keep in mind moving forward. That's going to tie in tomorrow. But the values on the X-axis that are relevant, the capital M sub I, to distinguish them from the lowercase m sub i's, are 1/2, 1, so we're ignoring the 0, 1, 3/2, and 2. The f of m sub I values, that was an attempt at a capital M, that did not work. So plugging them into the original function, 1/4, 1, 9/4, and 4. Multiply those by the delta x, just like we did on the other side. So 1/8, 1/2, 9/8, and 2. And then we find the sum of those. Oh, need my pen. So 10/8 is 5/4 plus 2/4 is 7/4. 15/4. So what we get from this, at least at this moment, because we haven't, I mean, I loosely connected it to integration, but we haven't done it in a meaningful way, is that we know that the area is going to be somewhere between 7/4 and 15/4. All right? All right, so go to the calculator, assuming I have one still.
Such trash.
But I also get home like next week. If I went there, like I would be home like next week, which is like for like that. And no one else is home. It's like boring. It sucks. Like there's no reason for
French.
It's all over.
Yeah, I'm not gonna.
Yeah, it's more absolutely. It's fine. You were substitute work out.
I gotta do this. All right, I'll just walk you through it, and then the video will appear on the, or I'm sorry, the calculator will appear on the video. So on your calculator, you're just going to hit program, because I wrote a program. All right, find the one that says Rex, R-E-C-T-S. You can imagine what it stands for. Yeah.
Yes, we can.
You.
My programs got all deleted. because,
Unfortunate.
Like, I don't know. One time I turned on my calculator and it wouldn't turn on, so I like opened the back and like pushed the batteries in to make sure they were in. And then I turned it on and all my programs would just disappear.
I will help you with that in a few moments.
Okay.
Can't find the Rex one.
It's on there. Rex. So it won't be this long.
Just keep scrolling. Just scroll.
Yeah, you scroll down.
I only have E.
Okay, well, you might be in the same boat, so we'll take care of you too. Select the program Rex, hit enter. It'll ask you what y1 is. That's the function. You're going to type in x squared and then hit enter. It'll ask you for the a value, type in 0. In this case, 0 is the a value and 2 is the b value. That'll change from problem to problem, obviously. So type in 2 for the b value. The n is the number of subintervals. So in this case, 4. And then T is for type. I'll just say left. This is the best I could do in terms of the programming. 0 is coming from the left, 1 is coming from the right. I figured 0 is smaller than 1. You know, it's to the left of 1 on the number line, so that would be your indicator. So coming from the left, I'll type in a 0, hit enter. It'll draw the curve first, then it's going to pause. All right, it'll have these like rapidly blinking dots in the upper right hand corner of your calculator indicating it's paused. Hit enter to unpause it. It'll create the rectangles. Hit enter because it pauses again. Hit enter to unpause it, and it'll give you the sum coming in from the left hand side. All right, then you could do the process again to come in from the right hand side, and then you get your approximation. So it is again x squared from 0 to 2, 4 rectangles coming in from the right. It'll pause and draw the rectangles and then give you the sum 3.75, which is 15/4.